since I think there been too many poles and zeros right from the morning, right? It's now time to do some light stuff. This is basically, so how many of you have taken a basic analog class before? Everybody almost, right? Okay. So, I will basically highlight something about very simple circuits that you most likely have seen before, and try to emphasize the fact that all these are indeed feedback circuits, and all these can be very systematically derived and understood. Per se, these circuits are not new or are not something which nobody knows. Okay, it's all very well known stuff. It's just a new way of looking at it and getting intuition, so that finally, when you want to do design, what do you need? You need to have intuition about how things work. Only then you'll be able to put things together, isn't it? So this is an attempt at doing that, and more importantly, I mean, this is not there in the textbook, so this is kind of hard material to find. Okay, so the basic problem that we all face at one stage or the other during design is to stabilize the bias current through a transistor. Why are we interested in stabilizing bias current through a transistor? You know that everything in the transistor depends on the bias current, correct? So GM is proportional to I, is dependent on I, okay, and the FT of the device depends on I, and all this stuff. So we want to make sure that the bias current in the transistor remains equal to I, irrespective of changes in the process. For example, the mu n Cox that you calculate on paper, right, may not be the true mu n Cox of the device when you make it in the fab. The VT of the device may change, correct? So the problem of bias stabilization is asking the following question: if I have a transistor given to me, what should I do? What VGS must I apply to the transistor so that the bias current remains equal to I? Correct? And this is quite something that you don't, I mean, when in a first analog course, you don't do this at all. You're doing the opposite thing, right? You're given VGS, find I. But in practice, in design, you do exactly the opposite thing, correct? I want I, tell me what VGS I must use, correct? In a transistor, what is the cause and what is the effect? VGS is the cause and I is the effect. So let's try and figure out what we should do. And the bias stabilization problem, as stated here, it basically is meant to indicate that I must be able to figure out what VGS I need to apply to a MOS transistor, so that when operating in saturation, the drain current is some reference, some known quantity I. And all right, so if you are in the lab, for example, what would you do? I gave you a transistor. I don't obviously tell you what mu n Cox is or what VT is. I gave you this box with 3 terminals. One is the gate, one is the source, one is the drain. Okay, this is the whole lab. Okay, latest equipment. Go and tell me what VGS I must apply to this transistor so that the drain current of the transistor, when operating in saturation, is 1 milliampere. What will you do? So forget taking notes and all, no more notes. Just relax. What will you do? I mean, plot the VI curves, okay, and then do what? Alright, let me ask you a similar question, right? You are driving a motorbike, okay? You want to go from here to there. This is the road. How will you, I mean, what angle will you apply to the handle? You can do many things. One thing is you can pre-calculate for, oh, this angle, if I turn the handlebar by 4 degrees and go at 40 kilometers per hour for this distance, then my motorbike shifts by so many degrees. Correct? Is that what you do? Or if you want to give somebody direction from here to say the loo downstairs, right? What will you say? Will you say go straight for like 11 meters, make a left, then go forward for another 3 meters, and then you'll get the door, then you make the right, and then you'll find the escalator, right? You walk 4 feet and then make a right. So that's definitely a good way of doing it, right? That's what GPS does, isn't it? I don't know how many of you have seen have cars with GPS on. Okay, it will tell you go 40 meters and then you make a left, and if the 40 meters is an error, then you know that you probably hit somebody. You understand? So that is an open loop way of doing things. Correct? So that's equivalent to saying, okay, I will take the MOSFET, I will measure its IV characteristics, and then from the IV characteristics I can go and figure out what VGS I must apply. These two are very analogous things. Correct? But is that what we do in practice when you give somebody directions? What do you say? You keep going straight, you take the first left, then you find the door, right? Then you make a right, you go down, you keep walking, you keep looking at your right, the fourth door is the, wherever you want to go. Okay? So what is the guy doing? The fellow who's heard the directions, what's he doing? He's at every point, if you think carefully, what he's doing is the following. He's comparing his position at the present point to the reference. So you've told him go straight and make a left at the first corner. So what is he doing subconsciously? He's comparing his present position with the position of the left corner, which he can see, correct? And then when his position, and he's driving, he's doing things in such a manner as to drive the error between his present position and the desired position to 0. Correct? So that's a feedback way of telling people to go from place A to place B. Right? Now if you take this to the MOSFET in the lab, what will you do? Will you plot characteristics, or can you do something smarter? Okay, a little simpler than that. I mean, if I didn't know anything, what will I do? I will apply some random voltage between gate and source, hope the MOSFET doesn't blow, alright. Put an ammeter, measure the current of the transistor, put an ammeter in the drain. If the ammeter reads 4 milliamperes, I need only 1 milliampere, what does this mean? It means that VGS is too large. Okay, and what should I do? Reduce VGS. On the other hand, if I find that the VGS, the drain current is only 10 microamperes, what does it mean? VGS is too small, I have to increase VGS. So eventually, I will reach a situation where the drain current is exactly 1 milliampere, right? And the VGS I have is the value I want. So let's think about this process for a couple of minutes. One thing we see is that this process will work for any transistor. I needn't know mu and Cox. I needn't know VT. Correct? So what does this mean? If I use feedback to figure out what VGS I need, then this will be a robust way of figuring out the answer, rather than plot characteristics, do mu and Cox, square root, blah blah. Does it make sense? Okay. All right. So stabilizing bias using feedback, which is obviously a very robust way of doing things, all right, involves the following tasks. You measure the quiescent current to the MOSFET, you compare it with the reference current that you wanted, and you kick VGS in the right direction. This is common sense, right? You didn't know any analog for this, and you've been doing this, in various aspects of life all the time. you compare, you measure where you want, you measure where you are, you compare where you want to be, and you kick yourself in the right direction, whether it's in your job or in your school or whatever, right? You want to get 90%, you have 5%, you work hard and get there, isn't it? So, all right. In a MOSFET, you want to measure current, right? So there are 3 terminals in the MOSFET. There are 4 actually, but we assume just gate, drain, and source. The 3 terminals. What is the? Can you relate the drain current to the I mean, so where all can I put my ammeter to measure the current? Drain current or the source current are the same thing, correct? So to measure current in the MOSFET, I can either stick an ammeter in the source or stick an ammeter in the drain. So accordingly, there are 2 places where I can measure the drain current. And I mean, it involves 3 parts, right? So first I measure the drain current, I compare the current with the reference, and then I need to kick VGS. I need to change VGS in the right direction. How many ways do you think are there of changing VGS? There are at least 2 ways of doing it, correct? To change VGS, I can keep S fixed and vary G, or keep G fixed and vary S. What is the third way? Don't think too much. And if A is a solution, B is a solution, vary both G and S. That's the third way, correct? All right. In analog, always think simple. Okay. So you can measure drain current in 2 ways. You can vary VGS in at least 2 ways. So there must be at least, the whole process of stabilization involves measurement and changing VGS. Measurement can be done in 2 ways. VGS can be changed in at least 2 ways. So there must be at least 4 ways of stabilizing the bias current in a transistor, correct? The first way will be measure drain current and change VGS by keeping, say, the source fixed and vary the gate. The second method is measure drain current, vary VGS by keeping G fixed and varying the source, the gate fixed and vary the source. Then you measure source current and change VGS by keeping the source fixed and vary the gate, and all permutations combination, correct? And you will see that we'll simply go through this. This seems like pretty common sense, right? It's not rocket science. This is what we do. Any practical guy would do. And the first thing to understand is that if you can describe any process in words, then you can always build a circuit to do it, right? So whenever you are given a design task, the first thing to do is what? Is to think carefully, right? Don't start by drawing transistors. First you understand, think carefully, and be able to verbalize in words what you want to do. And be rest assured that if you can clearly say something in English about what you want to do, you can always build a circuit to do it. And I'll show you pretty much how this is done in 3 or 4 examples. This is the first example. So, as I said, I'll quickly go through the slide. This is what we just discussed. I'll stick an ammeter in the drain, correct, to measure the current, and I must make sure that the device operates in the saturation region. So what should I connect what is the drop across the ammeter? Ideal ammeter should have 0 drop. So what is the potential at the drain? VDD. So I must make sure that the drain is connected to a sufficiently high potential so that it is operating in the saturation region. That's easy enough to do, correct? And I'll apply some arbitrary unknown voltage between the gate and source. Again, as I said, hoping that I don't blow the transistor. So when I apply a gate source voltage, some current will flow. I will be able to read that current in the ammeter. I will compare that with IREF. If ID is greater than IREF, then I conclude that VGS is too high and I must reduce VGS, and vice versa. We're all on the same page? Okay, we're all awake? Yes. Okay. Now, what do you understand when somebody says compare? When you compare your salary with your neighbor's salary, what are you doing? You are basically subtracting, isn't it? Okay. So when you compare two currents, what are you doing? The process of comparison is subtracting one from the other. How do you subtract currents? Do you think is a very terribly difficult thing to do, or is this a very easy thing to do? So two current sources, subtracting them is the easiest thing on earth, because Kirchhoff's current law will do that for you. You just connect the two currents in series, and basically you have subtraction. Correct? So to subtract two currents, what are we doing here? One is of course the drain current of the transistor, and then this is the reference current. I need to compare these two. In other words, I need to subtract the drain current from the reference current. Alright? Now let's look at the potential of this node Vx. If this current is exactly equal to Iref, what do you think will happen to the potential of Vx? If you have two identical current sources, the middle node potential, can we say anything about the middle node potential? Again, think carefully. The only thing we can say about the middle node potential is that this node, for example, the potential of this node will remain unchanged if this current is exactly equal to Iref. Okay? The only thing we cannot say is what that potential is, we cannot say. But this potential will remain unchanged. That's the only thing we can say. Correct? Alright. So, if this potential is going up, what do you think will happen? I mean, let's say you put these two current sources in series like this, and you monitor this potential, and you see it's going up. What does that mean? Yes, more people. Iref is greater than ID. Why? So, if you think about this node, the node potential is going up because more charge is being dumped into this node than is being sucked out of this node. Correct? So, if this potential is going up, it means that Iref is greater than ID. Correct? So, please note that we are interested in figuring out which of them is greater. Correct? And we can do that very simply by just monitoring the potential at Vx. If Vx is going up, it means that Iref is too high, which means that this guy is, you want to make ID equal to Iref, correct? If this node potential is going up, it means that the VGS we have applied is, if this is going up, it means that this current is smaller than this current, which means that VGS is too small, I must increase VGS. But I have decided that I am going to keep my source fixed, which means that I must increase VG. Correct? On the other hand, if I notice that this potential is going down, what will I do? I know that this potential is going down, it means that this current is too high, which means that this potential is too high. So I must reduce. Correct? So, what do you think is a reasonable thing to do? If this was going up, I needed to increase this. If this was going down, I needed to decrease this. So, a clean way of doing this is to simply, both of them are going in the same direction. So, I can simply connect one to the other. Correct? So, what does this mean? This is, I mean, have you seen this before? All the time, correct? So what do we see? The simple diode connected transistor is basically negative feedback system in disguise, right? Where what is happening implicitly is that the drain current is being continuously compared with the reference current, and depending on the error, the gate is kicked in the right direction, so that when everything is stabilized, this current exactly equals IREF. Okay. The same thing also holds for a bipolar transistor. Okay. All right. So let's go a little quickly now that you understand the basic idea. The next thing is we say, hey, measurement in the drain is not the only place I can measure the current. I can also measure the source current. I stick the ammeter in the source. Okay. And I say the only I'm going to basically, so the same idea, if this current is too high, it means that VGS is too large, I will reduce VGS and vice versa. Now again I need to compare currents. So what will I do? Let's say in this example I want to measure the source current. I want to measure the source current and compare it with the reference current and vary VGS by this time keeping the gate fixed but varying the source. Correct? So what do I do? How do I compare the source current with the reference current? Again I use Kirchhoff's law. I connect the two in series. Correct? So if the source current is larger than the reference current, what will happen to Vx? This node potential will increase because there is more current, the charge being pumped into this node than being withdrawn from this node. But if Is is greater than IREF, what does that mean? VGS is too high, correct? But VG is fixed, which means VGS is too high, but VG is fixed. So the source potential, which is also Vx, is too low, and I must increase it. Correct? And we can see that the very act of putting the current source in series with the very act of putting IREF in series with the transistor at the source is essentially accomplishing that. Correct? If this current is too high, then what does it mean? It means that this potential will go up, thereby squeezing the VGS of this transistor to a small, in a way so as to reduce the current and make it equal to IREF. Does that make sense? Alright. So the third thing is, this is basically what. The next thing is to say, hey, I can measure the current in the drain and go and vary the VGS by varying the source potential. So again the same old story, measure current in the drain, compare it with the reference, yank this in the right direction. If ID is greater than IREF, what should I do to Vs? If ID is greater than IREF, VGS is too large, which means that I must reduce VGS, but VG is fixed, so I must increase Vs, okay, and vice versa. And again, how do you compare currents without by getting? You obviously don't want to stick an ammeter every time into every transistor you see, right? So you compare the drain current with the reference current, monitor this node potential as usual, and if Vx increases with time, what does that mean? If this is going up, it means that IREF is greater than ID, which means that I must go and decrease Vs. Correct? On the other hand, if Vx is falling down, it means that I must increase Vs. And when should I stop this process? When this potential doesn't move. Correct? Okay, so if this goes up, I must pull this down. If this goes down, I must pull this up. Okay? So what do you think I should do? I need some kind of inverting amplifier. Correct? So in other words, I must compare this potential against a fixed potential correct, and kick the source in such a manner that if this goes up, this must go down. All right, and I mean, one way of getting making inverting amplifier is just use an op amp with a very high gain, correct. So in steady state, what will be the potential difference between these two guys? 0. And what are the signs of the op amp? This is negative or positive? It must be negative, because if this goes up, this must come down, right? And you can see therefore that you can synthesize the stuff. There is no confusion regarding the signs. It's obvious what the signs must be. How many of you have seen this way of stabilizing bias? Yes, 2, right? And this is this is one more way in which you can do this. Okay. How many of you have seen this one? Only one? Come on, wake up. Everybody, right? Okay. So the fourth one I will not discuss. It's actually pretty analogous, right? So you compare the potential at the source, then apply, when you compare the source current with the reference current and apply feedback at the gate. How many of you have seen this one? All right, so okay, so this is IREF. So we just discussed that this incorporates negative feedback, where the source current is compared to the reference current and you kick the source voltage in the proper direction. Alright, this is a pretty popular thing to do in ICs. However, on discrete, on a breadboard, for example, okay, on an IC it's very easy to get a current source, isn't it? You take a transistor, make it operate in the saturation region, and then you have a current source. And on an IC, transistors are free, but resistors and capacitors are very expensive. On a board, what is happening? Transistors are expensive and resistors are free, right? So if you didn't have to use a current source, what will you do? Okay, so if you're a poor man and can't afford a current source, what you can do is to recognize the following. I mean, you always know that no true current source will have infinite output impedance. So if this is I and this is R out, what is the Thevenin equivalent of this? R out in series with a voltage source of value IR out, correct? And when does this truly tend to becoming a current source? Okay, this will only become a current source. This will tend to an ideal current source when R out is infinity, which means that this arrangement will tend to a current source, ideal current source, when R out becomes infinity and this battery becomes infinite, correct? So as R out becomes larger and larger, this will become a better and better approximation to a current source. So what should you do? If you can't afford a current source, what you can do is you can do the poor current source, which can be approximated by which is basically this is minus I times R out and R out, correct? This is a replacement for, this is a drop-in replacement for this guy, okay? And if I make R out tend to infinity, this arrangement will behave like an ideal current. Is that clear? Okay. So what does this mean? It means like that this is connected to a negative supply of value, some VEE, which is a negative value. The value is actually minus IR out or something. But then nobody likes to have negative supply. So what can you do? You add, you don't like negative numbers, you add VE to everything, correct? So what happens? This goes to ground, correct? But what is the bottom line? The bottom line is that the drop across this resistor must be very small or very large. Earlier, what was this potential? It was minus I times R out, alright. There was some finite potential and R out was tending to infinity. So the voltage drop across this resistor must tend to infinity if you want to make it look like a current source. But what do you think is happening? I mean, if I add the same voltage to everything so that all the potentials are positive, what happens to the drop across this resistor? It remains the same. Adding a constant potential to all nodes does not change the drop across any one branch, correct? So this basically means that if you want this to work as well as a current source, you must have a large DC drop across the resistor. Okay, I don't know how many of you are familiar with this, but those of you, how many of you have seen this kind of biasing before? You have seen this, and what is the condition on I mean, when will this work well? Pardon? That's definitely true. Yeah. So basically, this will work well only when the GM times R out of the GM of the transistor times R out is much larger than 1. Okay. In other words, GM, what is GM of a transistor in relation to the bias current? 2ID by VGS minus VT. This times R out must be much larger than 1, which means that ID times R out must be much larger than VGS minus VT by. Okay. Alright, here also there is negative feedback because this is basically a poor man's current source. Okay. The moment this current attempts to increase for some reason, what will happen? This potential will increase, thereby squeezing VGS, telling the current to go back to its original value. Does it make sense? Okay. Should we just stop here, or we have, how much time do we have? 10 minutes? I mean, I can go on, yeah. So, all right. So the last thing I wanted to show is how simple transistor stages can also be derived from first principles based on negative feedback principle. So as far as the incremental circuit of a MOSFET is concerned, when a MOSFET is biased in saturation, if it's a good MOSFET, the output impedance will be infinity. So you can model the MOSFET as a voltage controlled current source, and in principle the GM can be as large as you want, correct? By simply burning as much current as you want, you can make GM infinity in principle. So let's see how we can put this to use. The first thing, I mean, see, in our basic circuits classes we have learned how to solve Kirchhoff's equations with linear elements, where the linear elements are basically R, L, C and the 4 control sources, voltage VCVS, VCCS, CCVS and CCCS. So our attempts, once we understand what a transistor is to basically start making the 4 control sources. correct? So let's start with making a voltage controlled voltage source with a gain of 1. And again, the question to ask yourself is, how will I make a VCVS with a gain of 1 if all I had is a variable current source? I mean, again, I push you into a lab, I gave you this big box with a knob on it. Okay, if you turn the knob, the current that flows between the two terminals of the box vary. Okay, and I'm telling you, I'm giving you this task. Here is a voltage V in. Okay, here is a load resistor RL, and here is a variable current source which you can vary mechanically by turning a knob on the box. And the task I give you is, I want you to make V in appear across RL, okay, exactly equal to V in, appear across RL, but with what? There must be some terms and conditions, no? If I don't, then you will simply short V in to V out. Without loading the input, right? That sounds like a reasonable task. Okay, so how do we go about this? No, I mean, well, if you know the answer, I guess, right? No, let's think from a common sense point of view, right? Before, I mean, all of us are exposed to this, so we know the answer, right? But if you had to think through this, assuming that you didn't know anything apart from, okay, can you use common sense to come up with the circuit topology? That's what I'm trying to drive. You have this variable current source. I want to make this voltage equal to this. What do you think I can do? Vary the current? So, in other words, what he's saying is that take this variable current source, push it into the resistor, correct? Then, obviously, there will be some voltage developed across the resistor. What is this voltage? If the current is I, the voltage is I RL. Then what will I do? I should compare it with V in. So, in other words, if IRL, which is V out, is smaller than V in, what must I do? If V out is smaller than V in, it means I is too small. What should I do? Turn the knob one way so that more current will flow and the output will become equal to the input. On the other hand, if IRL, so I must say if V out is less than V in, I must increase, no gate at this point, just a variable current source. That's why I said assume it's a mechanical box, okay, which you're turning. If IRL, if V out is greater than V in, what does that mean? It means I is too much, I must reduce I. Okay. So, in other words, this controlled source here, this is a controlled source, this is a current source which is controlled by what? I mean, actually you are sitting and looking at V in, V out, the difference, turning the knob. But in essence, what is it doing? Bottom line is that this current is being controlled by the difference between V in and V out. V in and V out. Correct? So, in other words, this is a voltage controlled current source where the current is being controlled by the difference between V in and V out. In other words, this is V in, this is V out, okay, and this is not, this is a controlled source. And this is a controlled source, so the output is current, the input it responds to is voltage. So what must be the dimensions of the constant of proportionality relating the output to the input? It must be of some form Gm times Vin minus Vout. Should it be Vin minus Vout or Vout minus Vin? If Vout is smaller than Vin, current must flow in this direction. So Vin minus Vout is correct. And when will Vout be exactly equal to Vin? I mean, so in other words, do you want to have a current source which only varies very little with change in Vin minus Vout, or do you need a current source here which is extremely sensitive to Vin minus Vout? You need something which is extremely sensitive so that it doesn't tolerate any nonsense between Vout and Vin. Even a small difference between Vout and Vin, the current, this guy, even if there is a small difference between these two guys, this guy is going to kick this node so hard that the difference becomes 0. Right? That's the sign of an accurate negative feedback loop. Correct? You understand? Okay? So, I mean, another analogy is like if the traffic laws were very strict, correct? And if somebody found you basically crossing a red light, then let's say they would take away your car and never let you drive again, right? Then what will you do? I mean, you'd think 100 times before going anywhere near a red light, isn't it? But if they say, oh, chalta hai, then, you know, you have traffic jam all over the place. You understand? So that's the role of the GM. Now, which is the transistor? No. This is the transistor. Because please recall that the transistor is a voltage controlled current source where the current is being controlled by the difference between these two nodes. So you can identify the transistor. This is the transistor. So where does the gate go? V in. The source goes here, the drain goes to ground. Alright. So do you recognize this incremental picture? What is this? The common, the source fault. You understand? So you can use the same reasoning to go and derive all the 4 controlled sources, and they all come out quite naturally without having to, I mean, the general tendency in the textbooks is to say common source, common gate, common drain, right, which is also the source follower, without any motivation for trying to do them, and often you're left wondering how the hell did this guy come up with this, right? And I mean, there's no need for all that mystery. It's actually, if you use negative feedback, you can and use common sense basically. Please know that I have not assumed anything, correct? Only thing needed here is we all only appeal to common sense, that's all. And you can generate all circuit topologies pretty much like this, okay? So obviously there's not enough time to go through all this stuff, but please feel free to go through the lectures, and also on our institute website there are recorded lectures of our classes, many of those which deal with this in a lot more detail obviously than is possible in a tutorial like this, but I hope you had fun, and so please feel free to get back to us with any comments or suggestions. Thank you very much.